Hello, my name is Gedaliah Knizhnik, and I'm presenting the paper, Flow-Based Control of Marine Robots in Gyre-Like Environments. It would greatly benefit research and conservation efforts to have lots of data about the ocean. But the ocean is big, and so measuring it requires either a lot of resources or simply making do with less data. On the other hand, ocean currents offer a free ride, so this makes the field ripe for robotics that can ride the currents to gather data over large regions. The problem is that riding the currents doesn't always get you to the most interesting spots. So a lot of work in the literature has gone into identifying how to move from current to current to efficiently get where you want to go. This, however, has so far required complete knowledge of the flow. This is a major obstacle because the ocean is very dynamic, and accurate models are incredibly difficult to obtain, which makes forecasting the flow, or even nowcasting it, very hard and inaccurate. So our question in this paper is, could you get away with less than perfect knowledge? In this work, we argue that yes, you can get away with imperfect knowledge. Take this double gyre, a common model used to describe ocean features. If we have an accurate model of this feature, then it is pretty straightforward to simulate the system and predict the path a particle will follow in the flow. But, as I mentioned, we may not have a model, and even if we do, it may not be accurate. But just from looking at this picture, imagine a satellite view with foamy features, I could draw this orbit onto it, where I've imagined there's no dissipation going on, so it's a closed orbit. And similarly, I can drop a pin on where the gyre center is, just by looking at it. Now these are almost certainly inaccurate estimates of the orbit shape and of the center, but if you consider the relative scale of the robot and of the ocean, chances are I'm pretty close. So what can we do with this knowledge? We can synthesize a controller. If we imagine there is no dissipation in the system, then there is a closed orbit for every orbital period. If a robot stays within the region defined by two such orbits, it will orbit the gyre at a periodicity within those bounds as well. Since we know where the gyre center is, our controller simply pushes out from or in towards the center to stay within those boundaries. We can apply this controller experimentally and see what happens. Here, we have a gyre rotating clockwise, and the region enclosing the desired periodicity is shown in red. On the left, we've animated the test with the green arrow showing thrust direction when the robot is thrusting, and on the right, we have experimental video with approximately overlaid boundaries. As we watch, we notice that the modboat thrusts only when it is outside the region of interest. It thrusts out when it is inside the inner boundary, and in when it is outside the outer boundary. All motion around the tank is provided by the existing clockwise fluid flow. The result is that most of our time is spent idling, during which time our robot could be running sensing tasks, communicating with other robots, or anything else we might want in a research setting. We're only actuating, at most, 30% of the time, and often much less. So not only can we ensure that we're getting the samples we want by enforcing an orbital period, but we can save energy while doing so, and at least triple the mission duration without recharging. Thank you for watching, and please reach out with any questions or comments.